Hi, I'm Paul. We're doing Leetcode must know interview questions. We are in the binary tree section of these questions, and today's challenge is path sum. This is rated easy, although I don't think it's any easier than the one yesterday, which was rated medium. What was the one yesterday? Flattening a binary tree into a linked list. It's really the same thing. It's a depth first search. In fact, if anything, I think this one, I don't know, to me, it's a little harder because you got to keep track of two things instead of just one. But anyway, the challenge is given the root of a binary tree and an integer target sum. Let me scoot this over so we see the method signature over here. The input is root and target sum. Return true if the tree has a root to leaf path such that adding up all the values along the path equals target sum. A leaf is a node with no children. All right, we'll look at that in a second. Any constraints to be aware of here? The value, the target sum, the only interesting thing, I guess, is the 0 here, which says that maybe the root input will be null, so we have to account for that. So here's an example. We get a root pointer to this tree, and we get a target sum, 22. And they've highlighted here that that there is a root to leaf path 5, 9, 20, 22 that equals the target sum of 22. All right. I want to kind of sketch through how that would work. Let me arrange this because I think I need a little bit more room. Okay, so we're going to do this with two stacks. Depth first search is done with a stack. We're going to do it with two stacks. It's possible to maybe do it with one stack, to keep the nodes and the sums in the same stack. Probably need to create a data structure for that. I don't know. I'm not going to do it that way because I just don't want to try to do it, on the fly and mess it up. Doing it with two stacks is a lot simpler. So we're going to have a stack for nodes, and we're going to have a stack for sums. Okay. So let's start with this stack over here on the left. This will be the nodes stack. We push the root and we push the value of the root. This is on the second stack. All right, once we've done that, then we drop into a loop, and we loop until we either find a target sum or we get through the whole tree and realize that there is no target sum. Okay, so the first thing we do in the loop is pop the stack. All right, we're going to pop the 5 node. I'm going to pop the 5 sum. I know there isn't really any visual difference here, but the 5 on the left is a node. The 5 on the right is a sum. I guess that'll be more obvious as we go along. Anyway, as far as finding the target sum, the first thing we do is check and see is 5 a leaf node, and we can tell if something is a leaf node by looking at the left and right pointers. If they're both null, then it's a leaf node. It has no child nodes. So 5 is not a leaf node. So that means we're going to start pushing things onto the stack. We're going to push the child nodes of the 5 node onto the stack. It doesn't really matter whether we push the right node first or the left node first, although in this case, because we can see the answer laid out in front of us, and if we want to find it faster, it's going to make sense to push the right node first. So we'll go ahead and do that. The 5 has been popped off the stack, and we're going to push the child nodes. That would be the 8 and the 4. Okay, over here, we are going to push sums. Okay, 5 is popped, and these are just integers over here. Push the sums. 8 plus 5 is 13. Push that. 4 plus 5 is 9. We're going to push that. All right. Erase these because they have been popped. All right. Next trip through the loop, we pop the stack, pop the 4 node, pop the 9. 4 is not a leaf node. So we will push the child node. I don't understand why it does that. We'll push the child node of 4, which is 11. All right. Push 11. Okay. Push 11. We popped the 9. And so we will push the sum of 11 plus 9, which is 20. All right. These guys are gone. They have been popped. Next trip through the loop, pop the 11. Pop the 20. 11 is not a leaf node. Okay, so push the child nodes. What did we decide? We're going to push the right node first. Okay. So get rid of the 11 and push 2 and 7. Okay. Get rid of the 20 and add 2 plus 20, which is 22, and 7 plus 20, which is 27. You can probably see where this is going now. Get rid of these. Okay. Pop the stacks. We get the 7 node, and we get 27. Now 7 is a leaf node. So we got to compare the sum with the target sum. The target sum is 22. This is 27. So that doesn't work. And 7 doesn't have any child nodes, so there is nothing else there's nothing to push. We'll just pop these off the stack. All right. Next pop, we get the 2 node, and we get a sum of 22. 2 is a leaf node, and 22 does in fact equal the target sum. So at this point, we're done. We found the target sum, so we return true. Again, there's 2 ways this can end up. One is we can find the target sum we can find a leaf node with the target sum, or we can go through the whole tree, not find the target sum, and return false. So let's look at an implementation. All right. First thing we want to look at is we've got a special case here, which is if the root comes in as null, then we aren't going to find a target sum. Okay, so we'll return false. We need to set up our stacks. So first of all, we have a stack of tree nodes. And we'll call that stack. Stack of tree node, stack equals new stack. Do that. I'm going to copy that. We also have a stack of integers. Let's call that sums. That is also a new stack. What else do we need here? Before we get into, yeah, we got to push. Okay, we've got to set this up by pushing the root node and pushing the root. I think it's called val. Let me double check that. Yeah, val. Okay. Push the root val. Now we can go into the loop. While not stack is empty. Well, the stack is not empty. If the stack is empty, we failed. Let's say tree node equals stack dot pop. Pop the node stack and int sum equals sums pop. Okay, we get the sums. Now, we don't really care about the sum unless this is a leaf node. So we got to check that. If node dot left, again, let me check these. I'm sure it's left and right is the names, left and right. Okay. If node left equals null and node right equals null, we can put this all together. And sum equals target. Get the name right. Target sum. Yeah, it's okay to do this. You're probably familiar with short circuit operators. If the left node equals null, I mean, we've got ands here. So if the left node is null, the if statement just stops there, returns false. If the if both nodes are okay, if both nodes are not null, it stops there and it doesn't check to see if the sum is equal to the target sum. Only if it's a leaf node will it check for the sum equaling the target sum. And if all of those things are true, then we'll return true. Okay, next, if node, I guess we decided to push the right node first. If the right node is not equal to null, then we will push the right node, and we will push the sum plus node dot right dot val. Okay. And I'm going to copy this. That wasn't good. All right. Same thing on the left. If the left node is not null, we are going to push the left node, and we're going to push the value of the left node plus the sum. All right. So we have two cases here. Well, we have one case so far, but if we find a leaf node that matches where the sum matches the target sum, we'll return true. If we get all the way through this while loop and we haven't found anything, then we're going to return false. And I think that's it. All right. Run it. Compile error line 25. Okay. Try that. Anything else here? No, that was it. All right. Run it again. Okay, base cases work. Put it over here and submit. And what do we have? Oh my God, it's not very good on the time. Wow. That's weird. That is weird. I'm going to submit this again just to make sure it's not like a glitch. No. 6.32. Huh. It's not very good. I mean, you could do this recursively, but I don't know. Maybe that would be faster. I wonder if maybe if we switch these again, maybe it's just maybe it is just a quirk. You submit it again. I'm very disappointed on that time because it's just like not much to the problem. Oh, again, 6.32 every time, 6.32. Well, I mean, it goes as a win in the scorebook, so you know, we'll take it 1 millisecond. So that's it. Again, it's a depth first search. If you go to a coding interview, you should know how to do a depth first search. It's not that you should know how to solve this particular problem. It's that you should know how to use a stack to do a depth first search. You should recognize this problem as being a problem that can be solved with a depth first search, and then write the code accordingly. I know there are binary tree problems, you know, coming up that use a breadth first search, which is done with a queue rather than a stack. But that's it for this one. I hope you enjoyed it. Please feel free to like, subscribe, comment, and see you next time.